So in this video we are looking at the condenser, and we're taking a look at it mainly from the perspective of what you're going to need in completing the assignment for the course. So first, a quick refresher from the lecture number 2. So the main role of steam condenser in a steam power plant is to condense the steam coming from the turbine back into liquid using cooling water, and that way we can pump the liquid water to high pressure without using too much power to do so. Condenser is always a tubular heat exchanger, so cooling water is inside tubes, steam condenses on the outside surfaces of the horizontal tubes and then flows down, collected in the so-called hot well at the bottom, and then pumped forwards as condensate. And in Finland, in condensing power plants, we basically always use some natural body of water as a coolant source. Only exceptions mainly perhaps some pulp mill sites where there might be clean cooling water supply at the mill, then you could use that. But other than that, always a natural body of water, almost never, well, not almost, but never a cooling tower. Back pressure power plants, CHP plants, cogeneration plants, however you wish to call them. If we are producing district heating, and about half of our CHP production is district heating, the cooling water is the district heating water, and it comes to the power plant at about 40 to 55 degrees temperature, and we heat it, depending on the season, to 70 to 120 degrees water, so that the heat customers can make good use of it. Now, the calculation, quick recap of lecture number 2 still. So this is the familiar symbol of a condenser after the turbine, and we remember that we always want to draw a temperature diagram whenever we are calculating any kind of heat exchangers. So very simple concept here: cold water comes in and it gets heated to some temperature going out as the steam condenses and releases heat. And we have condensate subcooling marked here, but typically that's very, very small, and within this course, unless you are told otherwise, it is safe to assume that the subcooling is negligible, and that means that the temperature of the liquid saturated water, and it is saturated at that point when there is no subcooling. So temperature 3 is the same as temperature 2. And temperature 2 has to be the saturated temperature at that pressure, and conversely, once we find the temperature at point 2 and we know the TTD, or terminal temperature difference, then from outgoing temperature we can solve what is the temperature 2, and then knowing that it is the saturated temperature, the pressure becomes fixed. So this way the condenser and the condenser heat transfer determines the end state and end pressure at the end of the turbine. So quick example to show how to go about this. So suppose we have a back pressure CHP plant producing district heat. We get return temperature of 50 degrees and we want to heat that return water back to 95 degrees Celsius supply water temperature. And our task is to solve condenser pressure when terminal temperature difference is 5 degrees. So what it means is that we've got the condenser, which is typically for a back pressure plant. It's a very conventional, ordinary U-tube, shell and tube heat exchanger. So our return water goes in here, gets distributed to all these little tubes. It's a U-tube heat exchanger almost always. So it means that there's just one tube that makes a 180-degree turn at the end, comes out heated, and steam comes to the shell side. It's distributed here, condenses on the surfaces, and liquid drain comes out at temperature 3. So first we draw the temperature diagram, and now, since we are not told otherwise, we can safely assume that there is no subcooling. Temperature 3 is temperature 2, and we are supposed to produce 95 degrees Celsius supply temperature. That's right here. We're told that terminal temperature difference is 5 degrees, so that means that the condensation has to take place at 100 degrees And we all know that the saturated pressure at 100 degrees Celsius is about 1 bar, 100 kilopascals. That's the temperature at which water boils. So as simple as that, and as we notice, the incoming temperature didn't really matter here at all. So if we really calculate heat transfer in detail, this also would have very small effect, but we're in power plant engineering course, not in heat transfer course. So for our purposes, it's good enough to consider that TTD and outgoing temperature, they define, and they always only define, but basically TTD is unaffected by temperature of water coming in. We can put it that way. So once we know outgoing temperature and TTD, temperature is fixed, and by saturated state, the temperature fixes the pressure. So then let's take a look at how the condenser affects the working of the whole power plant. So basically, what we just learned means that the coolant temperature that we have available pretty much defines the expansion endpoint. It fixes the pressure, and we remember that we pretty much know we want to be somewhere around 90% steam quality, definitely not too far below it at least. And if we know what is our fuel, that also means that our temperature, how hot we can heat our steam into superheaters without corroding the superheaters, that becomes pretty much fixed. So there is a range to play with, but it's not all that wide. What that means is that if we don't use reheat, there's not a whole lot of room for choice. So we can play around a little bit with the pressure and temperature here, and there is a narrow range of pressure depending on how much cooling water we pump in, so on and so forth, but really not very much. So what this means, we can again look at this through an example. So suppose we have a situation that we have 5 degrees Celsius seawater available for coolant, and that coolant gets warmed by about 10 degrees Celsius in the condenser, and our terminal temperature difference is 5 degrees. So this is a condensing power plant. Now we're supposed to evaluate the suitability of 530 degrees Celsius and 180 bar live steam values when we have turbine isentropic expansion efficiency of 85%. So how we go about this? First we need to find the condenser pressure, and we can do it with this data available. So 5 degrees seawater gets heated by 10, it goes out at 15, and steam condenses 5 degrees warmer than that, so 20 degrees. Saturated pressure at 20 degrees Celsius is 22 millibars, or in HS diagram units, 2.2 kilopascals. So that's our curve right there. Then we need to find our live steam point in the HS diagram. So 530 degrees Celsius plus 273, that makes 803 Kelvin. So we're moving very close to this 830 degree line. Pressure is 180 bars, so 18 megapascals. So somewhere around here we should have our cross. And we expand, we are doing all the calculation of the isentropic expansion efficiency and the curve. We can just draw it here, and we dive all the way down to 81.5% steam quality, so 18.5% of the steam has already condensed into liquid droplets. So that is too wet. Our turbine would not have a long and happy life in these conditions. What we can do here now, basically we could adjust the temperature, but as we were talking earlier, basically our fuel restricts us very much how much we can change the temperature. So we could maybe add a little bit, move further here, but not all that much. What we can do is change the pressure as much as we need to. So basically what this means is that the curve is what it is. It's defined by the isentropic expansion efficiency. Temperature is what it is. It's defined by the fuel, and pressure is what it is. It's defined by the available cooling water. So this line in about this kind of angle, we can move it right and left with the endpoints as if they were on rails at a given temperature and pressure. So now we need to move it to a drier direction. So we need to move it right. That means lower the pressure, and just looking at the diagram is a good way to take a guess how much we want to lower it. So let's say 80 bars instead of 180. Find the new endpoint. It's right over there. New expansion curve. Now we're at about 87-88% steam quality, and that's quite okay. So we can live with that and call it done. Now in your course assignment, you want to have a little bit drier steam, so rather more than 90%, because this part 1 of the assignment is going to be the basis of part 2, and you're going to have problems in part 2 if you get too wet steam already at this point. So try to have 90% and a little bit more. That should be a good value, and this is an easy way to do that. So basically what that means is that as temperature goes up or down, the pressure follows it. So we can, this is the same image as you have in your assignment instructions. So basically how you go about the assignment is you check your fuel. There's this other image where you can quite easily check what is a typical range of live steam temperature for that kind of fuel. You pick a temperature here, and then you can get a pretty good initial guess just from looking at here. You pick somewhere, suppose you decide that you've got the biomass, 500 degrees Celsius is a good guess for that. Then you start from somewhere roughly in the middle. That's your first iteration point. You draw the line on the ACES diagram, see where it ends up, and move it left or right as need be. And if you have municipal waste, then you get something very much lower. 400 degrees Celsius is very typical temperature for municipal waste, for example. And among biomasses, typically straws, there's a lot of chlorine and alkali metals, so you typically want to burn it a little bit. Well, you burn it at whatever temperature, but you want to keep the steam temperature maybe a little bit lower than you would with other kinds of biomass. But this is basically the idea of how to select the live steam values, and how the condenser really defines a lot about the whole power plant operation.